So now we can leave the floor to Julie, who we try not to do usually a topic generic. We try to do very various things, but it happened that today we will also have another presentation of another open source library. So thank you. Et le tapis, c'est là où il ne faut pas être.
Sorry. Thank you. Thank you for inviting me. I'm Julie. I'm a PhD student at inria Saclay in the SUDA team, under the supervision of Judith Abécassis and Gaël Varocco. The project that I will present today, it's a project that we've been working for the past few months with Vincent Maladière, Olivier, and my two supervisors. So we are working on survival analysis, but many of you, I think, don't know what is survival analysis. So first, I will introduce the topic, and then we will dive into our contribution to the field. So survival analysis is a tool to deal with right-censored time-to-event data. But what is time-censored, right-censored time-to-event data? So let's imagine you are conducting a study to see the effect of a drug, and you follow your patient for 2 years, maybe. Not all of your patients will die during those 2 years, hopefully. So for some of the people, you will just have the information that your patient is still alive until the end of the study, or maybe until a time where he or she has dropped the study. Why? Because maybe the complications were too strong, or maybe it's just like moved away or things like that. So you have like people, like you have data like that, and you see the event of interest. Here we will suppose that your patient dies, but maybe you can consider survival analysis in many domains, such as predictive maintenance, churn prediction, insurance, banking, etc. The goal, our goal, is to predict the CDF of their death to each patient in time. What do you use survival analysis instead of classification or regression? If you want to use classification, I know that you will die one day. And if I classify you in, for example, 80 years, you will almost surely die. But this is not my main interest. I want to really be able to, for a given patient, be able to predict the probability of being dead in 2 months, 6 months, 1 year, to be able to maybe choose the right treatment or things like that. And why can I do regression? Because what do I do with the censored patient? If I remove all of the censored patient, I will create a bias in my data because everyone will die, and that's not true. And if I just say that my patients are still alive, I will lie because I don't know what happened the next day or even a month after, etc. So that's why we use survival analysis. The notation here in this talk will just be like T star will be like the time of event of interest, such as the time of death, and C will be the censoring time. Obviously, I do not see T star, but I see T, which is the minimum between T star and C. I also have a second variable called delta, which is the event that has occurred. 0 stands that my patient has been censored, and 1 that my patient is dead. The only hypothesis that I will do is that I have non-informative censoring conditioning on X. Okay? So predicting the CDF of T star just means that I want to predict the survival function for each of the patients. That is to say, the probability that T star is higher than a given time, here zeta. So one way to deal with the censoring distribution is to consider the EPCW technique. The EPCW technique is the inverse propensity censoring weighting. And how you do that? You compute the probability of being censored, and then you reweight your patient. In other words, in the beginning, if I have information about you, it's only 1 point because everyone has the same probability of being in my distribution. But in the end, if you have a high probability of being censored and you are still in my cohort, it means that you have a lot of information and have to learn more about you. That is to say, I will wait more for the people that has a high probability of being censored. With that, I can just learn and evaluate models, things like that, with this technique. So the usual evaluation metrics in survival analysis are like 2 main metrics. First is called the integrated Breyer score. So it's really a metric to answer the question, how close to the real probabilities are our estimates. That is to say, if you are doing like some classification, it's like doing the MSE, but adapted to survival analysis. If, just to let you know, the weight is the weight of being censored. That's exactly doing a IPCW technique onto the probabilities. So it's a MSE for survival analysis. Here is just, we show, so in time, what will be our Breyer score. And then you just integrate it over time, and it has great properties. That is to say, the minimum will be the true probabilities. That's what you want to have if you focus on the probabilities. The other main metrics commonly used by practitioners is called the C-index. So it's equivalent to the ROC IUC, but in survival analysis. And the idea behind that is to rank the patient. So if a patient A will die before a patient G, I want to have the probability of dying to be higher for patient A for E, than for patient J, sorry. So you can it's really easy because you rank the patient and you can choose maybe which one is the more at risk. But recently in the literature, it has been discussed that you don't have really to chase the C-index. It's better to use like other commonly scoring rules like the integrated Breyer score, which focuses on the probabilities. If you obtain the true probabilities, you will have a great C-index, but the other way is false. For example, if all of the patients are well-ranked, I just add 0.1 probabilities to all of the probabilities. It will not change the ranking, but the probabilities will all be false. So it's better to focus on other metrics. So now we are really like diving into our subject. In our paper, we did not focus on survival analysis, but on the competing risk setting. So the main difference between survival analysis and competing risk setting is just that I consider more than one event of interest. For example, in survival analysis, I consider the death of the patient, but in the competing risk setting, I consider the cause of death. That is to say, you will only die one time, and you will only die because of one cause, and I have to choose which cause you will die of. So here are the main differences between survival analysis and the competing risk setting. Now, instead of having only one event of interest, I have big K number of events of interest. And I have to predict a big K CDF, cumulative incidence function. So that is to say, for each of the patients, I have to predict the probability of dying before tau and dying because of breast cancer, for example. So I will have like curves like this for each of the patients. And now what we see here is that we still have censored people, but we have like maybe dying from breast cancer, dying from heart attack, or things like that. So now what were the motivation of our work is that we wanted something that handles competing risks because we wanted to focus on different events of interest, but there are less results about it because it's a little bit much more complicated than survival analysis. Also, we wanted to predict the first event for each patient correctly. That is to say, really to focus on the probabilities and not focus on the ranking of the patient. Really, our focus was the probabilities. Finally, we wanted a good trade-off between the prediction and the fitting time, because actually we are doing like a project with the APHP hospitals, and they have not a lot of computational things. So it was really something that we wanted to have. And last but not least, something that handles tabular data well. So our focus wasn't on images; it was really on tabular data. So here is a title of our paper, Survival Model, Proper Scoring Rule, and Stochastic Optimization for Computing Risk, that was accepted a few months ago in ISTAT. So in this paper, we tackle the problem of computing risk by constraining a proper scoring rule. So what is a proper scoring rule? It's really simple. It's just that when you are doing like some machine learning algorithm, you have a score, maybe let's say MSE, and the better the score, the better the model fits the observation, and you're very happy. You just compare the probabilities that you have with the observation. The idea behind proper scoring rule is that if you are on the optimum, you have obtained the true probabilities. So it's something that you may want. So here is the proposition of our proper scoring rule for the computing risk setting. So you may recognize the weights that are like the EPCW weights, and then we are just doing a negative log likelihood onto the different classes. So for those who are familiar with multi-class, it's really like a loss in multi-class reweighted by the EPCW. Then we are doing this proper scoring rule at a given time zeta. So that's why you have like the one. It's just said that if your patient is dead before zeta, you're here, and if your patient has survived, you're here. This is a separable loss, and this can be given to any estimator that deals with that do stochastic optimization. So it was really the idea to teach a model how to survive. I can give it to gradient boosting trees, deep learning method, etc. But here we have implemented the loss with gradient boosting trees. Why? Because it has been proven, like in the literature, that for now gradient boosting trees outperforms deep learning methods. So what do we do? At each iteration of the algorithm, we sample a time uniformly between 0 and Tmax. Tmax is like the maximum horizon that you want to predict. And we stack it as a feature to be able to really predict continuously. Then we are computing like the EPCW weights and the target. The target is just that if my patient is already dead, and if he's dead, from what cause. And then I'm giving it to a gradient boosting algorithm, a simple one, the scikit-learn one, with big K plus 1 classes. The big K first classes represent the CIF. That is to say, the approximation of dying from one cause before zeta. And the last class is just to have survived until zeta. Now, to model C, we are just doing exactly the same algorithm, but instead of looking at T star, we are looking at C. And it's really like the same algorithm. And iteratively, with the feedback loop, once we train the cumulative incidence model, and one, the censoring model. So with our model, we made a big benchmark. So we benchmarked ourselves against like linear model with fine and gray, with tree-based model like random survival forest, and a lot of deep learning models. What we see here is that apart from us in the computing setting, no model are using like proper scoring losses, and only like 2 models that only deals with survival analysis are using proper loss as their loss. And also that not a lot of models can predict to continuous times. The metrics, we mainly use the mean integrated Breuer score, the C index, and also other metrics that you can find in the article. Here I will just show you the results that we had in the competing risk setting. So here I'm showing you the trade-off between the prediction and the training time. The lower is better for the mean of the IBS, and our model, sorry I don't have the legend, I don't know why, is here. So it's really great. And then you have to believe me that this one is also a tree-based model. That is to say, the two best models are tree-based model. This has been made on a real data set with 3 competing events and and 300K data points. We also did on the survival analysis benchmark, that is to say, with only one event of interest, and we compared ourselves against a lot of models. And what we see is that if you have like only a few samples, all of the models are practically the same, as you may see. But when you increase your data set, like for example 8K data points, naturally some model cannot scale. And here you see that this one is a survival competing game or something like that, already do not scale. So we really try to understand the scalability of each model, and that's why we did like this final benchmark in survival analysis, also on a real live data set called KKBox with 2.5 million data points. And we are just looking at the scalability of every method. Our method, SurvivalBoost, is trained with only 2 minutes for 100K data points and in 20 minutes for 2 million training data points. A lot of methods, even deep learning methods, do not scale. Why? Because they are doing something that is quite costly in terms of memory and time. So on our computer with another cluster, we cannot run those methods. For example, the tree-based method that I told you about that has really like great results, RSF, can only be trained with 100K data points. So we really answer the question on the scalability of those models. So finally, the Python library. It's called Hazardous, so we made this library with documentation, example, and some useful metrics, because we have seen that in Python there is a huge gap for competing risks, and that even the SAR index wasn't implemented in Python. So to conclude, here is the link of the paper. I've presented you a plugin proper scoring rule for the competing risk and the survival analysis setting. The implementation with gradient boosting trees due to the presence of categorical data really helped SurvivalBoost to have those results. And finally, outstanding performances in benchmarked, both in the competing risk setting and in the survival analysis setting. Thank you.
Thank you, Julie. It's really rare, I think, to hear about survival analysis, and also made with multi-class. Well, it's a sort of multi-class. So thank you for teaching us about this rare thing. Is there any question in the room?
Thank you for the talk. Could you just tell us a bit more about the application?
Yeah, so for example, we have been doing a project with the PHP data scientist team, and the project is about type 2 diabetes, and is to understand, for example, the role of the value of the monocyte on CV events. If you want to consider people that are dying from a cardiac event, you have to consider also the other deaths to be able to really have some results. So here, for example, you are interested in the competing risk setting. For some churn application, we have read an article written at Spotify because they wanted to know which clients were the most susceptible to just buy the premium account. In banking, it's I think it's for trading. So there are a lot of applications, and the multi-class is really because the difference between survival analysis and multi-class is that I consider in survival analysis that T star is independent of the censoring conditioning on X. And in the competing setting, I consider that the events are not independent. That is to say, if you are more likely to die from breast cancer, you may be more likely to die from heart attack because of the treatment or things like that. So that's why you cannot do survival analysis.
Is there any other question?
What is your opinion on the area precision recurve curve, AUPRC, precision recurve curve, as the indicator for a survival prediction?
It depends on what you are looking for. One thing is that you can evaluate with the ROC-AUC curve, but it will not give you the fact that you are really close to the probabilities. It's only like really the ranking that focus on that ROC-AUC is focusing on. So if you want to just know if your model can rank the probabilities, it's great. But I think that it's if you are working with a proper scoring rule, there are some properties. It's in expectancy, and if you've seen everything, etc., that it will give you a good ROC-AUC. But the inverse is not true. Some of the work that have been done just show that you can just play with your distribution and still have a good ROC-AUC. So it's really, I think it's great to evaluate one side of the problem, but to focus only on the ROC-AUC, it's not a great idea, I think.
Okay. And second question, for your benchmarking, have you tested only a fixed set of features so to compare all the prediction models? And I'm also wondering about feature selection. If you can compare the different algorithms.
I think that because the models are quite flexible, because we only use like machine learning algorithms that were quite flexible and deep learning models that were also big enough, we didn't really look at feature selection because we just let the model handle himself everything.
Okay.
We only tune the hyperparameters.
So far for your diabetes project, you haven't taken into account the competitive risk?
Yes. Yeah, we did 2 benchmarks.
Okay.
Actually, more than 2. But on a real life data set, we did 1 benchmark on the competing rate setting and 3 benchmarks on the survival analysis setting because it was harder to find data, the open data in the competing rate setting.
Okay, thank you.
Thank you. Do we have any other question? Yeah.
Thank you for your talk. Just one quick question. The proper scoring rule, how critical is it? And in practice, what is the impact of using a proper scoring rule? Thank you.
In practice, so just for you to know first, there are a lot of proper scoring rules that are well known. That is to say, the negative log likelihood and the MSE, or called the prior score, are proper scoring rules. So maybe you are using a proper scoring rule without knowing it. And then there are some properties that are really great, I think, about proper scoring rule, is that, for example, you can decompose your proper scoring rule between a calibration metric and an epistemic error. So naturally, you will also optimize the calibration of your model. That is to say, in the end, if you have like a great, if you are on the minima, you will have a calibrated model. So it's kind of cool, I think, to have this property. And then it's better if you want to really focus on the probability, to have a metric that measures the difference between your prediction and the observation, but the minimum are the true probabilities. So it depends on what you are looking for. But I think that because of the property of the calibration plus the decomposition of the proper scoring rule between a metric of calibration plus an epistemic error is kind of cool, yeah.
Okay. Thank you for this question, and thank you, Julie, and congratulations for having a paper at a grand conference.